Okay, so today we're going to be talking about 14.3, which is concentrations and rate laws. So the most important thing to know is that this is your equation for your rate and how it's affected by your concentrations. So on the left, you have your rate, which is going to be in molarity per second. Then you have the K value, which is your rate constant, which units will change depending on your concentrations, and we'll talk about that on the next slide. And then you have your reactant 1 and reactant 2, dot, dot, dot. But we're only going to have two reactants at most in this unit. And then they are two different exponents or orders as we refer to them typically. So, and the exponent we have is m and n, just to keep them straight. So your your rate orders, they're going to be typically low whole numbers like 0, 1, 2, or even 3, but we don't really have 3 very often because that means and anyways, the and these will sorry, the exponents are how much your concentration will speed up your reaction. So if your M value is 0, then your reactant 1 does not affect your rate at all. But if your M is 2, then the magnitude of the rate is doubled by your constant, or no, it's squared by your concentration. So that means it affects the rate a lot more. And then your rate order in respect to reactant 1 is the M value. So it's 0th order if it's 0, first order if it's 1, second order if it's 2. And then your same thing for the N in respect to reactant 2. And then your total rate order for your entire reaction is M plus N. So if M is 1 and M is 1 and N is 1, then overall this is a second order reaction. And a good general rule is that a large value of K, 10 to the ninth or higher, means a fast reaction, and a small value of K, 10 or lower, means a slow reaction. So basically, the larger your K is in respect to this, that the faster your reaction, and the smaller your K is, the slower your reaction. And this is how you determine the units of K. You have your units of rate divided by your units of concentration. So this example here is just for a second order reaction because your concentrations are in molarity, that's the units, and then your rate law is molarity per second. So when you find the K, you divide over your reactants, you divide them underneath the rate. So that's what's shown right here. You have your rate reactions up here, meters per second, and then for the second order, molarity squared. And for example, so then by canceling it out, you get m to the negative 1 and s to the negative 1. Your seconds will almost always be to the negative 1, so that's good to keep track of. But then, for example, if this was a first order reaction, you would just have m to the 1, and then your units would just the m's would just cancel out, and your units for that rate constant would just be s to the negative 1. And you should be familiar with how to solve these reactions. So let's do a three-step problem that is pretty typical to what you'll see on your tests. So this is your table right here, and you're going to find the rate law for this reaction based off the concentrations and the initial rates, the rate constant, and then the rate of the reaction when the concentration of A is 0.05 molarities and B is 0.1 molarity. And I'll give you a second to go solve that. Pause the video though, if you're going to do it, and then we'll walk through it step by step. Okay, so the first step to finding the rate law, here's all the work. So the way that I do it is I like to set up my steps in order. So first we're going to look at the concentration of B because as we see right here, A is constant. So we're going to look for when we look for the concentration of B, we're going to use it when A is constant and not affecting the rate. So that's going to be for steps 1 and 2. So if you put step 1 over step 2, then you can do the same with the rate. Put 4 times 10 to the negative fifth over 4 times 10 to the negative fifth, which is just 1. And then you're gonna put that on this side for the rate. This is just like your rate law equation, not rate, yeah, your rate equation, where you have rate over here and then your concentration right here. So then you do the same thing with the same order, step 1 over step 2. So you put point 0.1 over point 0.2 to get 1/2. And as you can see, the only way for 1/2 to an exponent to be 1 is when n equals 0. So um, B it the reaction of B is in its zeroth order with respect to the concentration of B. And then looking at A, we can go from steps 3 and step 2 because that's when A changes, and we know that B doesn't have an effect, so it doesn't matter that the B is changing for this one. So if we take step 3 over step 2, we get 16 to the negative 10 to the negative fifth time over 4 times 10 to the negative fifth, which is 4. So we're going to put that on this side. And then we have step 3 over step 2, or point 0.2 over point 0.1, and then we get 2 over here. Oh, shoot. 2 over here. And then we have m 2 squared equals 4. So the concentration of m is 2. So this is going to be a second order reaction, and your rate law is shown up here. Rate equals k, or the rate constant, times the concentration of A squared. Next, we're going to look and we're going to find k. So if you didn't do that already, do that right now, just by plugging in the concentrations and with a rate. So a way to do this is you just take from this first step, you plug in the A of point 0.1 and the rate, and that's shown right here. So your rate constant is 4 times 10 to the negative third, and the units are molarity -1, seconds -1. And then finally find a new rate for concentration of A equals 0.05 and B equals 0.1. And this is, you do this by using the same rate constant. So then you have your rate law, then you plug in your rate constant and then your A value, your A concentration, and you get the rate equals 1 times 10 to the negative fifth molarity per second. And that is a pretty standard problem that you're going to see. So if you don't understand that, just practice, and they're all going to be very similar to these, especially on your test. So good luck with the rate concentrations and rate laws.